Okay, the title of this talk is Representativity, Fairness in Clustering, and my name is Deepak. I'm the first author of this paper, and this is co-authored with my collaborator Savitha from IIT Madras, and I hold an affiliation with IIT Madras as well. So let's start with describing clustering and looking at what clustering is. So clustering is the task of grouping objects in a data set in a way that similar objects are more likely to be assigned to the same cluster. And this is arguably the most popular task in unsupervised learning. And unsupervised learning is the task of learning of machine learning where you don't have any labels to guide your learning process. And clustering enables us to find high-level patterns in the data set without having to go through all objects. There is a paradigm called CENTROID clustering, which was actually pioneered by the K-means formulation for clustering in 1967. And this one produces, along with every cluster, a prototype for the cluster. So K-means starts with an input parameter, which is the number of clusters that are desired in the output, which is the value of K. And it produces K clusters in the output given a data set, and it produces along with every cluster a prototype for that cluster. And in the classical K-means formulation, the prototype is simply the centroid of all objects within the cluster. And this may not be a real data point. So in cases where you need the real data, you need actually a real data point in order to make sense of the centroid, in order to make sense of the prototype, then you could use other variants of falling within the K-means family, such as K-midoid or partitioning around midoids. So let's look at clustering in a practical usage scenario, which is a scenario of job screening. So some job vacancies end up being heavily oversubscribed, right? Because in Indian Railways, which is a public sector organization in India, it's not uncommon for Indian Railways to get 100K applicants for each job posting. So manually perusing each job application may not be feasible at all. So the solution would be to use clustering to reduce the scale of the job, of the perusal job, of the shortlisting job from the number of applications that are available to the number of clusters. And we can simply do that using centroid clustering using the following pipeline. So we first represent all the applications in a space, in a task relevant space, which we show here as a 2D space. So each object in that 2D space is actually a cluster, is actually an application, a job application. And you do centroid clustering, and what you get is a set of clusters. And the clusters are color coded here. So there are a few clusters, there are a few applications that are assigned to the red cluster, a few that are assigned to the blue cluster, and a few that are assigned to the green cluster. And associated with each cluster is also a cluster centroid or cluster prototype, which is shown there using black dots. So now what you can do is to look at that application which is in the centroid, let's say the hypothetical application that is in the centroid, and make a decision as to whether that hypothetical application, the centroid application, needs to be shortlisted or rejected. In certain case, you might decide to shortlist, in which case you apply that decision that you make on the cluster centroid to the entire cluster. Similarly, in the case of other clusters, you might arrive at other decisions. So, for example, you could reject certain clusters entirely by looking at the prototype. And you could decide that certain clusters, certain cluster types seem quite ambiguous, so you might want to subject that to manual screening. So green for shortlisted, red for rejected, and the orange one for ambiguous, where you might want to subject that to more screening. So let's look at representativity as a frontier of fairness. So not all objects in the cluster are equally well represented by the centroid or the prototype. I'm using centroid and prototype kind of interchangeably here. So not all objects are equally well represented. For example, if you look at this cluster, I've zoomed in that cluster, and you have the red objects that are part of the cluster and this cluster prototype, which is the black object. In this case, let's consider two objects, A and B. And you can easily identify that just because of the proximity of A to the cluster centroid, to the cluster prototype, the decision made on the basis of perusing the centroid is likely to be much more suited to A, because it's much closer to the centroid than it is to B, right? So there is this frontier of unfairness. The decision made on the centroid is more suited to some of the objects which are closer to it than to some objects that are further away from it, despite all of them being part of the same cluster. So let's look at representativity fairness. So we call this frontier of fairness as representativity fairness. So you consider a vector representing a clustering over the data set where each object is associated with a proximity to its centroid. So you associate each object with a value, and the value is its proximity or dissimilarity to its centroid. So we would like this vector to be as uniform as possible. Ideally, we would like all values of this vector to be the same. However, that's not possible. So achieving total uniformity or achieving all values to be the same would require us to identify centroids such that all data objects live on an equal radius hypersphere, centroid as centered on the centroids. So that might be impossible, just because of the nature of the space. There is no such choice of centroids where everything lives on the surface of the hypersphere. So let's look at some ways of enhancing representativity fairness. We'll look at some toy examples here. The first scenario here, we're looking at just one cluster. In this case, it's a blue cluster, and the blue cluster has 4 objects, and its centroid is denoted by the black object over there. So, and we can look at the representativity vector here. So I've placed each of these objects, I've denoted each of these objects using their Cartesian coordinates. For example, 2, 1 is the object over here, and this is 1, 2, and this is 2, 3, and so on and so forth. And you measure the proximity of the object with that centroid, and then and in this case it's a dissimilarity, the distance, and you record it. So this is the vector that we are interested in ensuring uniformity over. So the average of the elements of that vector is 1.56, the max is 2.50, and variance of that distribution is 0.43, and the Jane measure, which is a measure of how uniform these entries are, is 0.88. Suppose we replace this centroid by a different object, by a different point, which I show as a grade point. In that case, and now we measure the distance of each of these objects to this new prototype, and then what you get is a different distribution. So that distribution looks like this. It's 1.412, 1.412 as against the earlier one, which was 1.12, 1.5, 1.12, 2.5. And if you look at it, the max is lower, so that's what we want. We want all objects to have to be proximal to the centroid, and the Jane measure, which is the uniformity measure, is higher, and the variance is lower. So just by moving this cluster prototype from here to here, you have enhanced the uniformity of this vector. The take-home message from this slide is that representativity fairness can be enhanced by deviating from the cluster as centroid, from the centroid as representative paradigm. So enhancing representative fairness, scenario 2. So let us consider, in this case, we have 2 clusters. Okay, so there is a blue cluster here, and there is a red cluster which contains only a single object, and the centroid is represented by a ring over the centroid, a black ring over the centroid. So now you have this representativity vector or the distance vector, and these are the values taken by it. For this object, which is 5, 5, you measure the distance to its centroid. Okay, so that is 0.0 because the centroid is right there. And for these, you measure the distance to their centroids. So you get this as the vector. Now you consider another scenario, which is where you reassign this object, this blue object, to the red cluster. So you now have two different clusters. Once again, have 2 clusters, but your centroids are different. This centroid is pushed back towards the blue objects, and this centroid, the red cluster centroid, is situated right in between the 2 red objects. So now you have another uniformity, another representativity vector, and as you can see, this is much more uniform than the earlier case. So basically the point here is that you can enhance representativity fairness by changing the cluster assignments as well. So the task that we have here is to perform clustering in a way that representativity fairness is enhanced in conjunction with the usual objectives, with the usual clustering objectives. We would expect a deterioration in overall clustering quality because representativity fairness is what we are trying to achieve, and that is not expected to come for free. So if we can achieve a configuration where the representativity fairness is enhanced much more than the overall clustering quality is deteriorated, is decreased, then we can claim some success. So that's what RFKM, or Representativity, Fairness in K-means, which is the name of the method that we propose in this paper. That's what this method seeks to achieve. So let's look at the RFKM objective. We don't go into the details of the optimization steps, but just talk about the objectives. So RFKM is based on K-means, but it adds two more loss terms to aid higher representativity fairness. So there is this usual dissimilarity term from the K-means objective function. So this is a standard K-means loss function. So this is the distance between the object x and its centroid. And for the K-means formulation, it's actually the square of the Euclidean distance. So this is the K-means loss. And for the second objective, you're looking at modeling the square of the K-means loss. So square of the object-specific losses. So why by doing this squaring thing, you're making it harder to maintain or to sustain the possibility of high dissimilarity to the centroid. So this is actually the dissimilarity to the centroid, x to its centroid, and when you take the square and sum it up, this objective function is better minimized if you minimize the larger sums, the larger values in that, and the larger values that are going into the summation. So it becomes, by taking the square, it makes it harder to maintain high dissimilarities. And in the second and in the third term, what we have is we explicitly try to minimize the maximum distance of an object to its centroid. So this loss captures the highest dissimilarity of an object to its centroid, and we would like to reduce the highest dissimilarity, and this is similar to what is called as minimax. And some of you might be familiar with Rawls's formulation of justice, where he talks about where it has been analyzed to be exceedingly similar to minimax. So minimax is basically trying to minimize the possibility of the maximally worst outcome. So in this case, it has that flavor because we're trying to minimize the maximum distance achieved by maximum dissimilarity across any given for any object to its centroid. So the hyperparameters lambda 1 and lambda 2 help to control the relative strength of the terms, and this is standard in formulations. So the max term, let's look at the max term. The max term that we saw in the third as the third loss term in our RFKM objective, it is hard to handle computationally, and that's because max is not differentiable. So we use an approximation along the following lines. We approximate the maximum of A and B by this particular thing. So here you can intuitively look at why this makes sense. You're multiplying each of them separately by a constant, and this is a positive large constant which is called phi. You multiply them separately. So in phi A, you exponentiate it, and phi B is also exponentiated, and the distance between A and B is exaggerated. So if you exponentiate a big, if A is slightly higher than B, then the e to the power phi A becomes much higher than e to the power of phi B. So essentially, when you exponentiate it and then add them up, the sum is dominated by this larger term, and you can recover that larger term by simply taking the log and then dividing it by phi. So it's fairly easy to see that even for moderately large values of phi, you get a fairly good approximation. So the RFKM steps mirror the K-means formulation itself. So it follows the framework of K-means. It estimates the cluster prototypes. They're no longer centroids under the new objective, but they're cluster prototypes, and the cluster memberships are estimated in turn. So you stop at convergence and output clusters along with their prototypes. And all the details of the formulation are in the paper. I'm just omitting those details for the talk. So we do an empirical evaluation, and our empirical evaluation makes use of a number of evaluation measures and baseline algorithms. So for evaluation measures, we look at two sets of evaluation measures. The first set is clustering quality evaluation. We look at how far it minimizes the K-means objective, which we call as the average. Well, it's actually the sum, but the sum is essentially the same as the average, because sum average is sum divided by a constant. And we look at Silhouette score, and Silhouette is basically a metric that measures the separatedness of clusters. And you also look at purity, measuring cluster adherence to external labels. And there is another set of evaluation metrics called representativity fairness metrics, where you're looking at the representativity vector and computing the variance as we did earlier, gain, which measures the uniformity, so you want high gain measures, and also max, which you want to be minimized because we're doing minimax here. We make use of a couple of baselines. One is the standard k-means, which does not have a representativity fairness condition, or which does not have an incentive to optimize for representativity fairness. And then the next baseline is what is called proportionality fairness, which is a recent paper. It has two variants. One is a local search method for doing the optimization, and the other one is a greedy method. The local search method tends to be faster. The greedy method makes use of data set level objective. It tends to be slower, and so on. And the data sets that we use for our evaluation are 5 data sets. All of these are public data sets from the UCI machine learning repository. They comprise a variety of different cardinalities. So Iris has 150 objects, whereas Letter has Avila has 21k objects, and a widely different number of attributes and widely different number of classes as well. So let's look at the representativity fairness evaluation. So we are looking at 3 representativity fairness metrics. One is the variance of the representativity vector, and the other one is gain, which measures uniformity. So you would want high values for gain, low values for variance, and also low values for the max. As you can see, so REKM achieves the best representativity fairness, and it is no surprise because it is designed to enhance representativity fairness, whereas none of them have that incentive. In particular, we achieve 18.6% improvement in the variance measure, and only 5.6% improvement on the gain measure, and around 46.8% improvement on the max measure. And you might see that the gain measure is between 0 and 1. So in the case of k-means, you're already seeing values of 0.84, 0.93, etc. So you really don't have so much of space or so much of leeway to improve upon representativity fairness. So gain is significantly different from the other measures. So your improvements are curtailed because it is because of its construction being between 0 and 1. And clustering quality evaluation, and as you can see, this is the k-means objective, and we are behind the best value. The best value for the k-means objective was obtained mostly by the k-means algorithm itself. We are behind it, 7.2% behind, so we take a hit there. And let me just go back to purity. Purity is about measuring the conformance against external labels, and as you can see, we are 4.12% behind. Purity is also like between 0 and 1. So we are 4.12% behind on purity, whereas on the case of Sill-Hart score, as you can see, we are actually surprisingly better on the Sill-Hart score. But Sill-Hart measures the separatedness of clusters. So by doing representativity fairness, or by enhancing representativity fairness, we're able to achieve more well-separated clusters. So which is kind of very surprising actually. But that's what we get. So we are optimizing Sill-Hart for free almost by just optimizing for representativity fairness. So the evaluation summary: we observed substantive improvements in representativity fairness. We obtained a small deterioration in clustering quality measures of average and purity, and surprisingly improvements in the clustering quality measure of Sill-Hart. And Sill-Hart measures the separatedness of clusters. And just to conclude the presentation, we have characterized a new frontier of fairness in clustering, which we called as representativity fairness, and we motivated why it is important in practical clustering scenarios where centroid clustering is useful. We outlined how representativity fairness can be enhanced through small changes in the prototype computation and clustering assignment stages, and we folded all these kinds of insights into a heuristic, into an objective function that forms the core of the REKM method that we propose. And our empirical evaluation illustrates that high gains in representativity fairness can be achieved through quite small deteriorations in clustering quality. So that brings me to the end of this presentation. If you have any questions, please feel free to contact me at deepaksp@acm.org.